Hi everyone, my name is Simran and I'm the marketing intern with Delta Q Technologies, part of the Zappy group of companies. I'd like to welcome you all to this session. Please remember that this session is being recorded and will be available to watch on demand following this session. If you have any questions during the session at all, please add them to the Q&A. You can find that tab to the right of your screen. Please note that these questions will be sent in privately. And with that, I'd like to introduce our speaker. I'd like to welcome Chris Botting, the Manager of Research Engineering at Delta Q Technologies, who will be speaking today about design trade-offs for battery chargers. Welcome, Chris. Please take it away.
Thank you, Simran. I'll just share my presentation screen here. So we'll be talking today about some of the common trade-offs with the design of battery chargers. As we walk through that, in particular, sorry, just a second here. Gotta love modern technology when it works. Okay, there we are. So we'll be talking about some of the trade-offs for the design of battery chargers. And as we walk through that, some of the topics that we'll cover will be some of the basic specs, like where the charger is located and what its power level is. Some of the trade-offs which are made with reliability, particularly for onboard chargers. We'll do more of a deep dive into size and cost, which is often where customer interest and the real hard trade-offs come. And then I'd like to also talk about some of the opportunities for system integration, which is actually where there are real opportunities to make 1 + 1 equal more than 2. I'm hoping that as you come away from this presentation, you'll be able to identify where the most critical trade-offs are for your charge system and gain some insight into what the priorities are in your application, because it really comes down to the individual needs of your application. But first, let's take a look at a case study. This is a bit dated, but most battery chargers in the past, and there are still many of them in the field now, tend to look like what's pictured here. So this is a 24-volt scissor lift. This is a photo taken from a local rental yard here in Vancouver, BC, in Canada. And this is a pretty typical old tech onboard charger. So as you can see, it's big and heavy. This is a ferro-resonant charger which operates at the line frequency. So it has a very large steel and copper transformer. As a result, it's inefficient, it's unsealed, it can't stand up to water or chemicals. And clearly this is a charger which has seen some of that in its lifetime. And it tends not to be very reliable as a result. The counter argument, which you'll hear from old time industry experts, is, but you can fix it. And we will circle back to this case study at the end of the presentation. Turning to basic specs like the location of the charger and the power level. And actually, before I continue here, I just want to throw up a quick poll on charger location. So just launching a poll here, just a very simple question. Where does your battery charger need to be located? Do you need an onboard charger? Do you need a offboard charger? Do you need both? And maybe if you have a range of products, or if you have different options, you may be selecting both. So as that pops up on your screen, just feel free to check onboard, offboard, or both, just to get a sense of the cross-section of who we have on the call here today. Okay, I'm just going to move to the next slide here, but I'll leave the poll open for maybe one more minute. Um, the um, i- in many applications, the charger is located off-board, and there are lots of benefits to this. If the charger's off-board, it doesn't add any weight or size to the vehicle. It doesn't have to go on board. So in theory, you don't care how much space it takes up sitting on a shelf, on the floor, or mounted to a wall. But this does really constrain the vehicle. This works well in an application, in a fleet application where you have vehicles that are coming back to a central depot or a charge station at the end of the day, at the end of a shift. But it doesn't mean that the vehicle can't just plug in anywhere that there's an outlet. This is typical in fleet applications, like for instance, golf carts. For onboard chargers, this gives you quite a bit more flexibility. You can really plug in anywhere that there's a AC source or an outlet which is sized for your charger. But now that the charger is on board, that means that size and weight, of course, matters. The charger has to be packaged in or on or under the vehicle or the machine. It also means that it's exposed to the environment that the machine works in. So it may have to withstand water or dust, shock, and vibe. The photo that you're seeing here is a floor scrubber, a floor cleaning machine, where the charger on the left there is located inside. The plastic lid has been lifted off to show the inside of the machine, but this means that the charger has some constraints on airflow. It's near some heat sources. It's near water and chemicals, and it's inside of a machine which has its own noise and its own vibe signature. There is also a third option, which we sometimes run into, which is to do both, or to have sort of a hybrid of onboard and offboard. In the floor scrubber on the left, for instance, there is a onboard charger, but the charger can be taken off. The battery can also be taken out and swapped. So in a high usage application, you could be charging batteries off board, and then you could be swapping batteries into the machine. You could also be keeping the charger and the battery on board, but you may choose to plug in when you're within range of an outlet. Even if you are operating the machine, you can charge either way. On the right, there's a motorcycle, electric motorcycle that has a standard smaller onboard charger, and then they also have a optional offboard charger. In this particular case, so these chargers can be paralleled. So if you're out and about, you can plug in with the onboard charger and charge slowly. If you come back to where you normally park, you have the offboard charger to add extra power and speed up the charge time. And in this particular case, some enterprising owner has actually added a compartment on the back so they can bring the offboard charger on board. So really, this is actually two onboard chargers. And if you look closely at that picture, they're actually both plugged in. I'm just going to switch back to our poll here, close our poll. And let's see what sort of results. Okay, so a lot of onboard and actually quite a lot of both. I'm seeing 1/3 are looking for onboard charger. A very small group, less than 5%, is looking for offboard. And then there's about 2/3 that both, which may mean that you need onboard and on and off board for the same product. It may mean that you have wide product lines and you have a variety of chargers which you offer there. I think that's typically what we see is that in some of the incumbent industries, there have historically been off-board chargers, but as they move to more modern chargers, the move is to move on board for all the reasons that we listed. So beyond where the charger is located, the next just basic question is, what is the charger power level? And this can be related to the charger being on board or off board, because the power level determines where you can plug in. If you have a high power charger, it's only going to be able to reach that power when you're plugged into a high power outlet or a charge station. So it just looking at this in rough terms, and this depends on the continent which you're located on, but in North America at 120 volts from a residential outlet, you can get about 1.4, 1.5 kilowatts from the wall. And when you factor in breaker ratings and the efficiency of the charger itself, typically your maximum charger power from a residential outlet is 1.2, maybe 1.3 kilowatts. In Europe and elsewhere in the world, running on 230 volts, you can get more power from a residential outlet. Typically that would be 2, maybe 2.5 kilowatts max. And then beyond that, when you start to get to 3, 6, 10 kilowatts up to 20, now you're talking a industrial plug, single phase for those lower powers, 3-phase for those higher powers, or a charge station, which the typical J1772 connector in North America is single phase, so typically 3 or 6, maybe 10 kilowatts from a 60 amp breaker. And in Europe, the Type 2 connector is 3-phase power, so now you can draw 10 kilowatts, maybe 20 kilowatts with 20 or 40 amp 3-phase breaker. So the choice of power level starts to drive where you can plug in. It may seem fairly straightforward, simple math, how much charger power you actually need. How big is your battery in watt hours? How much time can it take to charge in hours? And of course, if you divide, you get a minimum charger power in watts. So if you have a 8 kilowatt hour battery and it can charge in 8 hours, you need at least a 1 kilowatt charger, which is in practice means that you're going to probably have a 1.2 kilowatt charger in North America, or maybe a 2 kilowatt charger in Europe, so you can maximize draw from a residential outlet. And obviously, if you have a larger battery or a shorter charge time, you're going to be looking at higher power chargers. Often this is not so simple though, because if you have a range of options or a range of models in your offering, you may be offering different battery options. Maybe there's a small standard battery, but you can option up to add more battery range. Typically, that means that you have battery modules which are connected in parallel. You can do the same thing with the chargers too. Often there are options. There'll be a smaller standard charger, but there's an option for faster charge. And of course, if you're a vehicle OEM or a dealer, you may be looking to sell the higher end battery options and the higher end charger options, because those are going to be higher margin products. And there again, often a smart strategy is to be starting with a modular building block charger size, and then looking to add more chargers paralleled in the same way that you can add more batteries paralleled. This has several benefits. It becomes very easy to option up and simply add power, rather than having multiple chargers which you stock. A small, medium, large charger, you can have one SKU or stocking unit, and you just populate 1, 2, or 3, say, at the factory, or sell them through an aftermarket channel as an upgrade. Sometimes if you have tight packaging space, trying to fit these into a vehicle, it can be easier or more possible anyway, to fit several small chargers rather than one large charger. Sometimes the 3D package space which you have for the charger is not one large box, but it may be several smaller boxes that are distributed through the vehicle. Before we move on, I'm just going to pop up another quick poll here, again, just to get a sense of the audience, and that should be coming up on your screen there. What charger power do you need? And I've given lots of options here, and maybe more than one applies to you. That's fine. Just choose the option which seems the most representative. It's almost a logarithmic scale: 1 kilowatt, 10, 100, and up. At Delta Q, we focus on sealed chargers that are mainly on board, and our product range today goes from about 300 watts to about 1.5 kilowatts. We're currently launching a 3.3 kilowatt charger later this year, and we have the ability to parallel them to build charger systems up to 10 kilowatts, maybe 20 kilowatts, with up to 6 chargers parallel. But if you were on one of the earlier presentations, you heard our colleague from Scania talking about charging electric trucks and 18-wheelers in there. You know, he was talking about 80 kilowatts being a slow charge and 800 kilowatts being a fast charge. So that's a very different level of power. So I'm just going to press end poll here. We'll see the answers that have come in. Oh, we have a wide range here. Okay, so less than 5% is looking for less than 1 kilowatt, which sounds right. The real sweet spot is 1 to 3 kilowatts, which is over 1/3, and 3 to 10 kilowatts, which is also over 1/3. Then there's a smaller but still a solid group, 18%, that is in 10 to 100 kilowatts. So they're looking at EVSEs. You know, well, they're looking beyond the EVSEs and more into DC fast charger territory. And less than 5% is looking for over 100 kilowatts. So that'll be some of those Scania trucks, I expect. So that 1 to 3 kilowatt range, and then 3 to 10 kilowatt range, that's really where you see the break point between using a residential outlet maxing out at 1.5 to 2.5 kilowatts, depending on the continent, up to needing a single phase or even a 3-phase connection at an EVSE or a industrial plug. So moving on, we're mostly looking at, sort of medium power. From the sounds of the audience, we're mostly looking at onboard. And in particular onboard, but this is also true for offboard chargers in an industrial setting, you really need to be looking at the reliability. And that comes down to a few key things, which we'll touch on here: cooling, sealing, shock and vibration and drop. And of course, there are others. Sealing follows naturally from the power level. So at the lower power levels, you can passively cool with just a heat sink and natural convection. This is not applicable to higher power levels, but let's talk about it first because it has lots of benefits. It's very simple. It's very reliable. There's nothing to break. It's very cheap. It's quiet, and it is efficient. You're not spending any parasitic power running a cooling system. You have no moving parts. There's nothing to break. Now, the mounting orientation matters, and in particular, the mounting location matters. If you're inside of a machine that is constraining the airflow, if you're next to other heat sources, then passive cooling can become more challenging. There are other options. For instance, with passive cooling, there is the opportunity to not just shed heat to the air, but also potentially to shed air through conduction to a metal base plate if you're, for instance, mounted to the large metal frame of a vehicle. But typically, somewhere around 1 kilowatt or so, depending on the application, you're going to be looking to move up to a fan. A fan lets you decrease the size of the heat sink pretty substantially and bring down temperatures, which can help with the reliability. But it adds cost. It adds noise, and a small amount, a modest amount of power draw. And now you have at least one moving part. So that's a potential failure mode. fans are not going to be suitable in some dirty uh, usage applications. Dust can be a problem, particularly for a unsealed fan. Mud, even if it doesn't obstruct your fan, it can start to choke up the heatsink and degrade its performance and choke some of the passages in between the fins. If you're under a vehicle, particularly a highway speed vehicle, you'd start worrying about things like gravel bombardment, which can crack the plastic blades, or the fan shroud there may now need to be metal rather than plastic. And there are all sorts of dirty environments, both indoors and outdoors. One story which we've run into from the field was we had some customers who were using one of our fan-cooled chargers in a factory, actually in a meat rendering plant. And so we discovered that chicken guts, raw chicken guts, are not good for fans. Lots of lessons that you learn as the rubber meets the road and products run into the ground truth of how they're actually used. Somewhere around 6 kilowatts or so, and this is really going to depend on the application, but there is definitely a break point where you start looking at liquid cooling. This has the smallest size, so you can get the highest cooling performance and the highest power density, but it greatly adds to the cost and the complexity of the system. And this is typically going to make sense if you're already part of a larger vehicle powertrain, which has an onboard cooling loop to cool larger devices, like a liquid cooled motor and inverter, or maybe a engine or battery pack. Thinking about this from a reliability point of view, and also from a FMEA, from a failure mode point of view, there's a lot to like about passive cooling. Fans can fail, liquid cooling can fail, and here, water and electricity do not like to mix. So not only does your charger need to be sealed, but you also need to make sure that your cooling passages and your power electronics are sealed from each other, structurally, and also at the connectors and as they're serviced. So talking about sealing, particularly in an outdoor or a wet environment, but as we said, you can run into water or chemicals or pressure washing and other liquids in an indoor usage as well. Probably you're familiar with the ingress protection, or IP ratings. IP65 spray, IP66 is a high pressure spray, like a pressure wash. IP67 and 68 get into submersion in water for at least 1 meter and 30 minutes. And there can be some subtleties to a blanket statement that a product is sealed to a certain IP level. Is it sealed? Is the fan waterproof? Are the connectors waterproof? Are they waterproof when they're mated? Are they waterproof when they're unmated? These can affect how the product stands up. If water gets inside, does it have a way to drain out? Is there a Gore-Tex or some other membrane for pressure exchange so that you can handle sudden temperature changes or changes in the altitude or shipping on an airplane? Closely tied to sealing then is corrosion. If you're going to run into water, you're also likely going to run into salt or fertilizer. We have a lot of chargers in golf and lawn care sort of applications, and they run into lots of chemicals. Of course, also solvents, battery acid, and moving beyond chemicals in any application, you have to be asking if your plastics in particular can stand up to ultraviolet light. Are your labels going to be legible after 10 years? Are your displays going to be still nice and transparent and not discolored or opaque or fogged up after years spent outdoors in the sun? one of the other major categories when it comes to the robustness of a charger is shock and vibration and drop. I spent about a decade in the automotive bus and truck market, and I was surprised in some ways coming into some of these industrial markets that they actually had more aggressive shock and vibe specs from the point of view of the average and the peak values of the G values. This can come from driving over bumpy terrain, but it also comes from driving in vehicles that have solid tires, that don't have suspension. If you're in a fully loaded forklift and you're driving at full speed through a warehouse where the floor has been made of multiple concrete pours, every time that you drive over one of those breaks in between floor pours, or you drive, in or out of a room or a freezer, you may be going over a pretty substantial bump. And then in some applications, you may have specific vibration tuned to a particular resonant frequency or to the operating frequency of an onboard motor or pump, which you may be actually bolted to. Drop is an interesting one. You certainly want your charger to be able to survive a drop onto a concrete floor. What you're seeing there in the picture is a fairly typical golf course charge barn. So you got rows of golf carts. Normally they would be packed in pretty tightly. There's actually lots of empty rows here. This is probably after the golf carts have mostly gone out for the day. And there's a whole fleet of chargers overhead, standing about 10 feet off the ground. Actually, in this particular photo, these are fairly old tech. Those look to be fairly heavy ferro-resonant line frequency chargers. Those are probably 10 or 20 kilograms each. And if one falls on your head, that's going to be a bad day. So we've certainly had some golf cart barn hands tell us that they love our chargers because they're lighter when they fall off the shelf. 1 or 2 kilograms versus 10. But chargers on shelves or suspended overhead, they can be easily pulled down if a vehicle drives away while it's plugged in. In a good application, you typically have a drive interlock signal, which disables the motor controller when it's plugged into the charger. But even if the vehicle plugged in can't drive away, another vehicle could be driving by and could run into the cord, or what we call a drive-by, where it gets pulled out. So size versus cost. One of the constants of being a battery charger maker is being asked if the charger can be smaller and also if it can be cheaper at the same time. And sometimes that's possible, but often there's a trade-off there. So let's dive into that a bit. So it may be useful to think of power density as having sort of a sweet spot. So what I've shown here is cost on the y-axis versus the power density, which is basically just the size on the x-axis. And the shape here is similar to a bathtub curve, which you may have seen if you've looked at failure rates of components, where early in life, as you come down the left side of the bathtub, there are infant failures. In midlife, there's sort of minimum point, the flat bottom of the bathtub where the failures are low, and then late in life you start climbing up the right hand side out of the bathtub again as the failure rate goes up with wear out failures. And there's sort of something similar going on, particularly with sealed chargers when it comes to the energy efficiency. So with a sealed charger, and this is very different for unsealed off-board power electronics. Like if you're buying a power supply that's a rack mount for telecom or UPS backup power, it's very different when you can blow a fan through an open frame box. But when you have a sealed box and all of your all of the loss which you generate, all the heat has to come out by conduction. Whether you have liquid cooling, fan cooling, or passive cooling, you have to conduct all of that heat to the outside of the box. So the size of the box and the size of the heat sink, particularly when it's passively cooled, is going to be driven in large part by the efficiency. And let me just turn on a pointer here. So starting on the left-hand side, as you drop into the bathtub, this is where some of those old tech chargers come in. They're very inefficient as a result. They have a lot of steel and copper, a big heat sink, and just a lot of weight. So there's a lot of cost in the size. The electronics may not be particularly expensive, but the overall cost is high. And as you move to more modern switching power supplies, you can really reduce the size and the cost at the same time. So that's the good news, but only up to a point. Because at a certain point, if you're going to further increase the efficiency, you will have decreasing returns with the reductions you can get of the packaging and the heat sink, and you're going to start to face increasing costs of the power electronics. So if the key really is to kind of find out where you want to be on this curve. You clearly don't want to be on the left-hand side. In a low-cost, high-volume application, maybe you want to be right in the middle, at that middle point. If you're making a electric motorcycle, you're probably going to be looking to somewhat climb the right-hand side. There's going to be some cost premium that you're willing to pay for increased density, but there are still limits. So looking at this from a historic point of view, one of the main ways that you can decrease the size of a charger is by increasing the switching frequency. And the last 20, 25 years have really seen a revolution in the battery charger industry. The main story there being moving from line frequency chargers, which operate at, the 50, 60 hertz line, to switch mode power supplies, which typically operate at least 3 orders of magnitude higher. So a typical switching frequency goes from 60 hertz to about 60 kilohertz. And with that 3 orders of magnitude increase, there has been a substantial, maybe about a 2 order of magnitude decrease in the volume of the transformers and the inductors, of the wound components. And that's why with those old ferro-resonant chargers, like the photo at the top, half of that box and almost all of its weight is taken up by a very large 60 hertz steel and copper transformer. Whereas the charger that's below it is the charger which is now used in the field, and the actual transformer there is about 100 grams. Now, moving forward into the future, there are still gains to be made here, but there are definitely diminishing returns. So we can move from about 100 kilohertz to maybe a megahertz. Maybe we can go beyond that. Some of the wide bandgap devices are promising, gallium nitride and silicon carbide, as we move beyond silicon MOSFETs. But there start to become other trade-offs and other effects, which we'll talk about on the next slide. There's not a Moore's law for power electronics the same way that there is for processing power. And really the reason for that is, processing power can get arbitrarily small until you run into the atomic scale, because you're not actually doing any work. You're moving ones and zeros. But here, we're actually processing watts, and those watts, are represented by physical currents and voltages, and there are actual losses tied to that. So past a certain point, your transformer stops getting smaller, and it mainly starts to get hotter and more expensive. One of the things we can do as we move to higher switching frequencies is soft switching. So most power converters are hard switching, and what that means is shown by those sort of classical switching waveforms on the right. Um, you have voltage across a switch and no current, and then when you turn the switch on, you have current and no voltage. But in that transition period, depending on the speed of the switch, you have overlap between voltage and current, and that's where you have loss. Those switching edges are also where you have EMI, where you create electromagnetic noise and interference. And these losses increase with the frequency. So if you double the switching frequency, you have twice as many of these switching instances and you double the loss. Now, one way to get around this is to move to resonant converters or soft switching, which means that you switch when the voltage or the current are at zero, so you don't have overlap or much less overlap between the voltage and the current. And what that typically means is that you have a resonant circuit, which so rather than those square wave forms, you have sine wave waveforms. So the current naturally commutates back to zero, and then you can switch. So in the last decade or so, since about 2010, these have started to come to market in the battery charger industry. I think one of the leading soft switching or resonant battery chargers was the Delta Q IC650 shown on the right, where the output DC-DC converter is a LLC converter, which just means it has a resonant tank formed of L, and C, two inductors and a capacitor, which resonate together, forming that sine wave current, so the current commutates naturally. But the input AC-DC converter is still hard switched. And even as you move from silicon devices to GaN and silicon carbide, there are limits. There are still switching losses, and you start to have trade-offs with EMI. I won't get into some of the other mechanisms like fringing fields and the proximity effect and core losses, but there are reasons that it's hard to find a free lunch here beyond a certain point. One of the next things which you might look at is losing the diodes. So there will be diodes in both the input stage and the output stage of a charger, because you basically, every time that you rectify from alternating current to direct current, you're going to pass through diodes, and there'll be fixed losses where the diode has a fixed forward voltage drop, and the loss is proportional to the current passing through it. Now, you can get around that if you replace the diodes with switches in what's called active rectification, or sometimes synchronous rectification, because you operate the switches synchronous with the current. And if you can select switches which have a low on resistance, then you have a much lower voltage drop when there's current passing through. This can cut losses in those diodes by as much as, say, 90%. But it adds cost because the MOSFETs cost more than diodes. It adds complexity because now you need gate drive circuits, and maybe you need to isolate them. You need to control them. And it may also add failure modes because diodes are very robust to surges and to load dump events, and MOSFETs, you may have to react very quickly to a surge in the line or the load. But this is an opportunity, particularly where you have low voltage and therefore you have high currents. So on the AC side, particularly in Japan and North America with the lower input voltages, a bridgeless or a totem pole power factor correction circuit may make sense. At the DC output with synchronous rectification, this may make sense, particularly with 12 volts, 24 volts, maybe 48. You can still have synchronous rectification in a 400 volt system, but at that point, you're no longer talking about saving 2 or 3% efficiency. You're talking maybe 0.5% or marginal gains. And the reason there to have diodes may be about having bidirectional capability, being able to push power from the vehicle battery back to the grid or to a load. And then finally, maybe one of the most practical ways to increase power density is simply to try to make better use of the three-dimensional space. A typical charger design starts with a single planar circuit board, but if you start adding horizontal and vertical circuit boards that are at right angles, and if you start to be able to get some of your bulky through-hole components to have similar heights, you can really pack things together. This also has limits and challenges. So what you're seeing on the left there is a typical modern, I think this one's actually gallium nitride based USB-C power delivery charger for a laptop or a phone. The assembly can get tricky. So the assembly labor, some of the manual processes, if you look closely, you'll see that some of those components have isolation tape wrapped around them so that parts that are live can get closer to other live parts. That's a cost. It's also a manual process, which is hard to control. Shock and vibe can be challenging. It's fine in a small charger like this, but at a larger scale, when you're connecting these larger masses at right angles to each other, you're going to put stresses on the joints of those circuit boards because you're essentially creating mullet arms when you go through a shock, a vibe, or a drop event. Cooling can become challenging too. It's much easier to cool something which is flat versus a three-dimensional shape. As we said, creepage and clearance of some of the live parts, and then finally the electromagnetic noise. You can often get more and more crosstalk as you push some of these parts closer to each other. So again, a promising approach and one that we use at Delta Q, but there are also practical limits. But I want to talk about where there actually, I think, are opportunities to make 1 + 1 = more than 2, and that is system integration. So at a high level, the idea is can we integrate the charger with other components so we can save cost or size or weight? And I'm not talking about necessarily saving cost, size, or weight of the charger alone, but taking other cost, size, or weight out of the system by deleting other components or integrating them, or by adding value by adding other features. The first thought people usually have is to integrate with the battery. This makes sense. You've got a battery and a battery charger, and there are cables in between them. So why can't I just plug my battery into AC and it charges? And certainly at a system integration level, you should be looking to tightly integrate the charger with the battery from a control and a data point of view. And also you should have a charger supplier who's working closely and coordinating closely with your battery maker or your BMS maker to make sure that they're talking well, that they're compatible, that you're maximizing charge time, life, and safety. But actually physically integrating the parts can be problematic. And it really comes down to thermal reasons. With a charger, and this is particularly true when it's passively cooled, we typically want the charger heatsink to run as hot as we can so we can minimize the size. If we have to constrain the charger maximum temperature to a lower value, that's going to increase the size of the heatsink. And the battery usually has the opposite goal. They're looking to keep it cool or around room temperature to maximize life. A battery is an electrochemical device, so the usual rule of thumb applies that for every 7 to 10 Celsius increase in the battery temperature on average, you cut the calendar life in half. So you would not want to have a 20 Celsius battery next to a 60 or 80 Celsius heatsink. Either you may raise the temperature of all the batteries, or worse yet, you may raise the temperature locally of just certain cells, and now the battery is going to age in a unequal way. The photo which you're seeing here is the battery compartment out of a scissor lift. So this is a swinging out or folding out box. And the charger and the batteries are in the same box, but you'll actually notice there's a steel bulkhead between them and also some space. And that helps to thermally isolate the batteries from the charger. The next thought is usually the motor controller, and sometimes with this, the motor. This is possible, and I've seen this done. Um, there are more papers and prototypes than there are products in the field, and there's a reason for that. There are some clear benefits to reducing wiring and size and integrating software, but it's possible to share the power electronics. It may even be possible in some cases to use the motor windings as some of the inductors, for instance, as the boost inductors for the charger. But this can compromise the efficiency and the performance of both the charger and the motor controller. It can also cause problems with safety and isolation, with EMI. It can even cause problems where if you're making use of integrated motor windings when you're charging, there's the possibility of unintended torque. So the vehicle could move while you're charging, which no one wants. But where this may make sense is sharing the heatsink and the fan. You don't typically charge and drive at the same time unless you have a very long extension cord. So it may make sense to share, packaging, wiring, and the cooling. Now, what may be more promising is integrating the charger with a DC-DC converter. There's often a higher voltage traction battery and a lower voltage, for instance, a 12 volt or a 24 volt system that may have headlights or controllers or other loads on it. You can certainly put a battery charger, you can certainly put a DC-DC converter into the same box as a battery charger, and right off the bat, you can have some savings in packaging and cooling. Once again, those loads are often off or at least reduced during charging, so it may be somewhat complementary in terms of the heatsink. Here, it actually is possible to share some of the power electronics as well, and Delta Q has some patents in this area, which we're implementing in our new 3.3 kilowatt charger. What you're seeing there in that functional drawing is the central box. There is our DC-DC converter for the charger. So the actual power converter, which takes AC from the line and converts it to, say, 48 volts for a battery. It's possible with some relays to reconfigure it so that the traction battery is connected to the input, and your auxiliary system, say your 12 volt loads, are connected to the output. And now you're reusing the same electronics to serve a second purpose. This works best if those auxiliary loads are off during charging, or if they're low. It's also possible, and this is something that we're doing in our new charger, to have some smaller dedicated DC-DC converter that's paralleled with this so that you can still support some of the hotel loads. For instance, keeping a BMS powered. Moving on from some of the larger functional blocks to more integrated features, certainly makes sense to integrate a charge station interface. And I'm not talking about actually having a EVSE be physically part of the charger, but rather integrating the circuitry that you need for some of the handshaking, the pilot, the proximity, the actuator signals, so that you have a charger on a vehicle or a machine that it can now charge from global standard EVSEs. So this is something which Delta Q has built into our new 3.3 kilowatt charger. ZVAN with our parent company Zappi also has some chargers that have built-in EVSE interfaces. And for some of our older products or our more cost-sensitive products, we also have a standalone module so that you can have one module which can control one charger or a group of parallel chargers so that it can enable that charge station interface. And finally, CAN bus, and this is true for other serial buses, but CAN is the common standard. This can be very helpful as well. Obviously, there are lots of things that you can integrate with over CAN, including talking to a BMS, but a CAN display can be very useful. It provides a unified user interface, looks very professional and clean, much more so than wiring this up ad hoc with wires, buttons, and a remote LED. Not only can you display the charge status and faults, which you might display on a charger's front panel, but you can start to display and control information which is harder to put on a simple LED and a button, like the ability to change battery charge profiles if you need to manually trigger and equalize, or if you replace the batteries and you use a different make, model, or a different battery chemistry. And finally, this is just a sampling, but there are lots of other opportunities. We've got some customer examples here, like a vacuum cart, where similar to the scrubber that we showed earlier, the onboard charger can switch seamlessly from charging the battery to powering the vacuum motor and still keep track of what the battery state of charge is. In some golf cart systems, we supply a DC connector system, where in this particular case here, there's 2 pins for DC positive and negative, and then on the 3rd pin, we can actually multiplex multiple functions like status LED, spark lift disconnect with a first break, last make, drive interlock for drive away issues, and in particular BMS charge control, or with a lead acid battery, a connection to a onboard temperature sensor. So let's just circle back to that case study with that rusty old tech charger that we looked at the beginning. So what's on a modern scissor lift? Often it's a Delta Q charger like the one shown here. So much more compact, sealed, and rugged. It's more efficient. It's more reliable. We've moved away from the paradigm, but you can fix it, to it doesn't break. It turns out it's better to have a non-serviceable charger that doesn't need servicing. And we've been able to add some customer value with a user interface and data logging and charge profile changing, which was not present on the older charger. So just closing out, I hope that you take away a few things here. Really, the main thing is you need to understand the requirements of your application. And everyone's application will be different. So the priorities which you make when you're choosing a charging system or when you're choosing a charging system vendor is going to really depend on what your application is. Generally speaking, paying more for reliable hardware upfront is going to pay off in total cost of ownership and in customer satisfaction. Power density is what we often get asked about, and there is continued progress there, but it comes with some trade-offs. And then finally, system integration really is where you may still be able to find a free lunch and reduce system size and cost, or add features and value. So that said, do we have any questions?
Right. If you guys do have any questions, feel free to add them to the Q&A tab on the right hand of your screen. All right, I guess I'll just get this ball rolling here. So thinking about reliability, what's a typical design life for a battery charger?
Yeah, so it's going to depend on the application, but at Delta Q, we would typically design for maybe an 8-year design life, or a 5 to 8 year design life, which means that the product in the field should be lasting more than that. So typically, if you're looking to offer like a 5-year warranty, you're going to want a design life that's about twice that, like a 10-year life. And we do pretty extensive validation testing on our products to prove that out, so that we can stand behind some of the warranty times that we offer. So that 10, 12, 15-year life, which a vehicle could be used in the field or might be resold or go through a second life, the charger should be lasting through that. And we typically validate using a statistical statistical method with a sample size, so that we have a confidence level, a statistical confidence level in the life which we've designed for, so we can stand behind our warranty.
All right, awesome. Yeah, thank you. Still no questions. Again, feel free to just put them in the Q&A tab. But if not, what is the power level that's required to switch from a single phase to a three-phase AC power?
Yeah. So again, this may depend on the continent which you're on, but typically single phase power will be appropriate for 3 kilowatts and 6 kilowatts, certainly in North America with a EVSE. Once you start to need 10, 20 kilowatts, it's simply going to have to run on 3-phase power. And there are some chargers out there, particularly in the automotive space, plugging into the EVSEs, which may be designed to operate off single phase in North America at 6 kilowatts and off of 3-phase or 2 of the 3 phases at a 3-phase supply in Europe. I just got a question here. What is the best way to manage 3-phase power charging in Europe? That's an excellent question. I think it's going to depend on whether you're plugging in a public or private setting. In a public setting, if you're able to rely on the public charging infrastructure, you're probably going to be wanting to plug into a Type 2 connector, which has 3-phase plus the neutral. So typically, most of those have a 20 amp breaker. So you can draw 60 amps from a 20 amp breaker with 3-phase. That means about a 10, maybe a 11 kilowatt charger. Less common would be 40 amp 3-phase breakers where you could draw 32 amps from each phase, and then it's 20 or sometimes 22 kilowatts. So 10 or 20 kilowatts from the public charge station infrastructure, and of course, in a warehouse, in a industrial setting, it's going to depend on the power which you have installed. And if you need to do DC fast charging, then it's not going to be plugging into an EVSE.
All right, awesome. If there's no more question, that pretty much wraps up our session. So thanks again to Chris for our presentation and insights, and to you all for joining this session. So yeah, that wraps up the session on design trade-offs for battery chargers. Feel free to join the Delta Q Expo booth or other sessions in the lobby.